Hello my dear students, welcome back to our physics class. In the last class we had seen angle of twist and angle of shear for a cylinder of cylindrical rod or wire of length L and radius R. Today we are continuing the topic by deriving the twisting couple on a cylinder. So again here also we consider a cylindrical rod of length capital L and radius R, whose upper end is fixed, and we are applying a twisting couple at the lower end in a plane perpendicular to its length. So what happens when we apply a twisting couple? Due to elasticity of that material, a restoring couple will develop inside the material, which will oppose the twisting couple. The last classes we had seen that whenever a body undergoes a deformation by the application of a force, there is an internal reaction force that will develop inside the body due to the property called elasticity. And this internal force is opposite to the applied force. So here also we are giving a twisting couple at the lower end of the cylinder, and inside the material a restoring couple is set up which opposes the twisting couple. And you know that at equilibrium the two couples balance each other. So this is the picture of a cylindrical rod or cylindrical wire which we have, and we are going to find out the expression for the twisting couple. So first we are considering a solid cylinder. So a cylinder, we can imagine this cylinder to be made up of a large number of cylindrical shells. So we can see the cross section of a cylinder in the picture. So we can consider this cylinder having length L and the radius small r to be made up of a large number of cylindrical shells. And we are considering such a cylindrical shell of radius x, thickness dx, and length L. So the cylinder is made up of several shells, and we are considering only one such shell. In the second figure you can see that shell, and its cross section is of a circle, and in that shell the considered shell is having a radius x, and that shell is having a thickness dx. Now as the rod is twisted, you can see a line AB drawn on the surface of the considered shell, and what happens when we rotate the shell at its lower end? the line AB will rotate through an angle phi, and now the position B will becomes B dash and the line AB will become AB dash after applying the twisting couple. So that phi is known as the angle of shear, which we had discussed in the last class. Now the angle formed by B when it had a displacement to B dash is theta, and that theta is known as angle of twist. So theta is the angle of twist at the lower free end of the rod. Once again I am explaining the cylinder. We have a cylinder of length capital R and radius small r. Its upper end is fixed and its lower end is given the twisting torque, twisting couple. Now we had considered this cylinder made up of a large number of cylindrical shells. See, we know that the cross section is a circle, isn't it? But we are considering it along its length. So the cylinder is made up of several shells, cylindrical shells, and we are only considering such a shell having a radius x and thickness dx, and we are drawing a line on the surface of that shell, and that line is AB. Now what happens to AB after giving a twisting couple on the lower end? This AB gets displaced to AB dash, and that angle, that is BAB dash, which is equal to phi, is called angle of shear, whereas the angle through which B gets displaced to B dash is called theta, which is angle of twist. So here you can see two angles, angle of shear phi and angle of twist theta. Now you can write two equations for this. We know that angle is equal to arc by radius, isn't it? So let's consider phi. Phi, the angle phi is equal to arc by radius. Here arc is BB dash and radius is the length of the cylinder capital L. So you can write phi is equal to BB dash divided by L. Now again you can apply the equation, that is angle is equal to arc by radius in the case of theta also. That is theta is equal to angle equal to arc, that is BB dash divided by radius. Here radius is the radius of the shell which we had considered. So the radius is x. So theta is equal to BB dash by x. So we got two equations from the relation angle is equal to arc by radius. So BB dash is equal to L phi and BB dash is equal to x theta. So you can equate these two equations and can find out phi as x theta divided by L. Now let F be the tangential force acting on the base of the thin cylindrical shell. So we had considered a shell having radius x, thickness dx and length capital L, and the tangential force acting on the base of this shell is considered as F. So the tangential stress is force per unit area, that is area of the base of the shell. So force is F. Now how we will calculate area. So that shell is having a radius x. So its circumference will be 2 pi x. Now its thickness is dx. So multiplying the circumference with the thickness will give you the area of the base of the shell, that is 2 pi x into dx. That is expression for tangential stress. Now what is the rigidity modulus of the material of the rod? that is stress by strain, isn't it? The corresponding tangential stress to tangential strain. So we have the tangential stress as F by 2 pi x dx. Now what is the shearing strain here? Shearing strain is phi. Now we had derived the expression for phi as x theta by L. So we can substitute for phi and can find out the value of rigidity modulus of the material of the rod, that is FL divided by 2 pi x square dx theta. So we had got an expression for rigidity modulus, isn't it? We are going to find out the twisting couple of the cylinder. Now from this equation we can write the expression for force as F is equal to, you can simplify it in your notebook and can find out the value of F as 2 pi n theta by L into x square dx. So we got the force, isn't it? Now what is couple? Force into distance will give you the couple or moment of the force. So the moment of the force about the axis of the rod, or which is also known as couple, is equal to force into distance. Here force, we had got the expression for force, and the distance is the radius of the shell which we had considered. So the radius of the shell is x. So F into x. So the equation will be 2 pi n theta by L into x cube dx. So this is the expression for the couple, twisting couple. That is a couple required to twist the considered shell of radius x and thickness dx through an angle theta. That is the twisting couple required to twist the cylinder or to twist the shell through an angle theta. So just we had considered only a single shell of the cylinder, isn't it? We have to calculate the total couple of the cylinder. So how we will calculate the total twisting couple? By integrating this expression. From where to where we will integrate? See, the variable is dx here. Dx means the thickness, and thickness, or we can say that it is the distance to the shell, or it is the radius of the shell, isn't it? The maximum radius can be the radius of the cylinder itself. So the integration will from 0 to r. So 0 to r, 2 pi n theta by L into x cube dx will give you the value of total twisting couple on the rod. Now integral x cube is x raised to 4 by 4, and you can give the limit as r and can simplify it and will get the value of total twisting couple as pi n r raised to 4 by 2l into theta. So this is the total twisting couple on the cylinder, which is the couple required to twist through an angle theta. Now substitute theta is equal to 1 radians. What does it mean? It is the twisting couple per unit twist. Theta is equal to 1 means it is twisting couple per unit twist. That will be just substitute theta as 1. Or you can take theta to the left hand side. So what will happen? Twisting couple divided by theta. Now what is theta? Theta is 1. That means it is the twisting couple per unit twist. So it will be pi n r raised to 4 by 2l, which is given as the variable c that denotes the twisting couple required to produce unit twist. And this twisting couple, we know that it is equivalent to the restoring couple, isn't it? So the C is now also known as restoring couple per unit twist, or it's also known as torsional rigidity. that is the restoring couple per unit twist or twisting couple required to produce unit twist, is known as torsional rigidity. So we got the expression for the twisting couple, also the twisting couple per unit twist. Now we had considered a solid cylinder, isn't it? Now we are considering a hollow cylinder. A hollow cylinder means it will have an internal radius and an external radius. Internal radius R1 and external radius R2. So how we can integrate? See, you remember we had integrated the solid cylinder from 0 to R. But in the case of a hollow cylinder, we have an internal radius R1 and an external radius R2. So from where to where we have to integrate? From R1 to R2 we have to integrate that expression. So we will get pi n theta by 12 into R2 raised to 4 minus R1 raised to 4, where R1 and R2 are the internal and external radius of the hollow cylinder. Now again we can define C. C is the couple required to produce a unit twist, isn't it? So theta is 1 here. So the expression will be pi n by 12 into R2 raised to 4 minus R1 raised to 4. That is the couple required to produce a unit twist. Here it is denoted as C dash. So in the last slide we had got an expression for C, that it is pi n r raised to 4 by 12 in the case of a solid cylinder, and here we got it as a C dash, that is pi n by 12 into R2 raised to 4 minus R1 raised to 4. Now we can compare the both cases, that is solid cylinder as well as a hollow cylinder. So we are having two cylinders, one hollow and other solid, and both the cylinders are made up of the same material and having the same mass and same length. And we already know the couple per unit twist for the solid cylinder as well as for hollow cylinder. How can we compare these two? Just divide C dash with C. What you will get? Pi n by 12 will get cancelled, and what remaining? There is only the radius terms remains. So C dash by C will give you R2 raised to 4 minus R1 raised to 4 by R raised to 4. And the numerator can be simplified like R2 square minus R1 square into R2 square plus R1 square divided by R raised to 4. So we have got the ratio of couple per unit twist, C dash by C, C dash as that of a hollow cylinder and C as that of a solid cylinder. Now we are going to simplify the right hand side. How we can simplify the right hand side? For that we are considering that these cylinders are having the same mass and it's just made up of same material, isn't it? So we can equate the mass of both the cylinders because the masses are the same. Now how we will equate the mass? We know that the mass is density into volume. By the relation, density is equal to mass by volume. So mass is density into volume. See, so the material is, both the cylinders are having the same mass. So we equated the expression of mass in the case of both the cylinders. And since it is made up of same material, the density will be the same for both the cylinders. So we can take the density as a rho itself. Now what is volume? We know that a cylinder having a radius r and length L will have a volume pi r square L. So you can equate the mass of a solid cylinder with that of a hollow cylinder, and the left hand side you can see it is pi r2 square minus r1 square into L into rho, that is the mass of a hollow cylinder, which is equal to pi r square L into rho, that is the mass of a solid cylinder. Now pi L rho get cancelled. We had taken rho as density. Since the two cylinders are made up of same material, it is having the same density since it has having also the same mass. So L and rho pi get cancelled. So we have r2 square is equal to r square plus r1 square. Now we can give this equation to our previous equation, that is C dash by C, and it can be simplified. You can do it by yourself and you can simplify it and can have the equation C dash by C as 1 plus 2 r1 square by r square. Now how can we analyze this equation? See, C dash by C gives you a term that contains 1 plus 2r1 square by r square, isn't it? That means 1 plus 2r1 square by r square is greater than 1, isn't it? That means C dash by C is greater than 1. If C dash by C is greater than 1, C dash will be greater than C. So that is the result we need. That is, C dash is the twisting couple of a hollow cylinder. Thus, C dash is greater than C. What does it mean? If two cylinders, one hollow and the other solid, of same mass, length and material are given, to twist the cylinders through the same angle, more torque will be required for the hollow cylinder. We had got that C dash is greater than C. C dash is the couple per unit twist. So theta is the same for both the cylinders. But even though theta is the same, C dash is greater than C. That means the torque or the couple required for the hollow cylinder is greater than that of a solid cylinder. So more torque will be required for the hollow cylinder. Or we can think it in the form of an application. A hollow shaft can transmit larger torques, or it can withstand larger torques for the same angle of twist. Or we can say that a shaft in the form of hollow cylinder is more stronger than a solid shaft. So it's an application level question. The shaft in the form of a hollow cylinder is stronger than a solid shaft. You can explain it with the help of the derivation which we had done. It's a simple. Just have the values of C and C dash. Take the ratio between them and substitute for R2 square. Simplify and you can find out C dash is greater than C. So it's an application level question, very important. Now the last small topic, that is a work done in twisting a wire. We had already seen that this work done is stored as the potential energy, isn't it? That potential energy is known as the energy of strain. So here we are going to find out, we have the value of C. C is the couple per unit twist, isn't it? If C is the couple per unit twist of the wire, what is the couple required to produce a twist theta? It will be C theta, isn't it? Once again, C is the couple per unit twist. Unit twist means their theta is equal to 1 radian, isn't it? Now, what is the couple required to produce a twist of angle theta? it will be C into theta. Now what is the work done? Work done in twisting the wire through an angle theta. So we are going to twist the cylinder to an angle theta. So we can do the integration from 0 to the maximum angle of twist, that is theta. So integral 0 to theta c theta d theta. And integrating theta, you will get theta square by 2. So the expression is half c theta square. Now you can substitute for c, that is a couple per unit twist, and can rearrange it and can find out the value of work done in twisting the wire through an angle theta, that is pi nr raised to 4 by 4l into theta square. So this is the total work done in twisting the wire or rod through an angle theta. And this work done is stored as the potential energy of the wire, which is known as the energy of strain. That's for today's class. Let's go through a summary. We had found out the twisting couple for a solid cylinder, twisting couple per unit twist for a solid cylinder, a hollow cylinder, and we had done the comparison between them, from where we found that a hollow shaft is more stronger than a solid shaft. And also we found out the expression for work done in twisting a wire, which is also known as the energy strain, since the work done is stored as the potential energy of the wire or the rod. Thank you.